It's a generalization of both Bell-type scenarios and these Kochen-Specker type scenarios. So for Bell-type scenarios, you might want to think of there being many different experimenters at many different locations, and they perform measurements and get outcomes at these locations. While in Cochen-Specker scenario, typically you'll be looking at a single site, but you'll have sets of compatible measurements that you can make at these sites, at this one site. I'd also say that this formulation is quite useful for looking at possibilistic models or negative probability models. You're not restricted to just looking at probabilistic models, and we've had some interesting results in these things, but I won't elaborate on those now. So more precisely, we have a finite discrete space of measurements that we can make. And then we have some sets of compatible measurements, so the measurements that we can make together. We call these contexts, and the contexts form a cover over this measurement space. We also have a set of outcomes, and we have an event presheaf. So what the event presheaf does is it takes any subset of the measurement space and it gives you all of the possible assignments you could have for these measurements. Okay. So now we define no signaling probabilistic model as a compatible family of probability distributions over these contexts. So over the things in the cover of the measurement space. So compatibility is actually, it's exactly no signaling. I won't go into this here because we don't really need to use it. But that is true. This thing, the support presheaf, we are actually going to use here. So the support of a no signaling probabilistic model determines a sub-presheaf of the events. And what this sub-presheaf does is it takes, for any subset of measurements, it tells you what are the assignments that get non-zero probability for the model that we're thinking about. Okay. So this is actually what we're going to use, or something derived from this one when we're looking at cohomology. Now, so just to give you an example to kind of help you understand what's going on here. This is the support of the PR box, which is an example that will be familiar to a lot of you. So here the measurement space is these things. So we have two A measurements, which we think of as Alice's measurements maybe, and two B measurements that we think of as being Bob's measurements. So the measurement contexts are these things in the leftmost column. The allowed measurements here are when you have one measurement from Alice and one measurement from Bob. I've written these as tuples just so that I can match up the outcomes of the measurements. So these are the outcomes, and each one in here corresponds to a section that is in the support. So something that gets non-zero probability. If we were to look at the fully probabilistic version of the PR box, so not just the support, we'd actually get halves everywhere here. So we'd actually have a distribution over each context. Okay, so that's just to give you an idea of this measurement setup. Now, a couple of definitions. We say that the model is possibilistically extendable if every section is a member of a compatible family of sections. So where we pick one section from each context, and the sections agree on restrictions. So, for example, these two have an overlap on A. So if we pick a section from here and a section from here, they should agree on the A assignment. Okay, so we say it's possibilistically extendable if every section is a member of a compatible family of sections. And this is our notion of locality. So actually, if this is violated, if we have possibilistic non-extendability, this is a sufficient condition for non-locality, or contextuality, if you want to say. Further than this, we have an even stronger type of non-locality. This we call strong contextuality. So there's a kind of a hierarchy here strong contextuality sits above possibilistic non-locality in this hierarchy. What strong contextuality says is that no section belongs to a compatible family of sections. So we can start with any section that's in the supports, and by looking at this we will discover that it can't belong to a compatible family. There are models where some sections belong to compatible families and others don't as well. So we'll see an example of that shortly. Okay, to say a few things about the Cech cohomology. So, as I said already, cohomology seemed like the obvious tool to use to look for obstructions. There is this issue that Cech cohomology is defined only for abelian presheafs, and the support presheaf that we were working with doesn't have this structure. So what we did is we freely put Z linear combinations over things in the support presheaf, just to form an abelian structure. Okay, so what we do is we associate for each section an element of a particular cohomology group, and I didn't want to get into too many technical details on this time I have, but for those of you who are familiar with this stuff, maybe it's useful to note that this is the group. It's relatively okay. And finally, the last thing I want to say about the mathematical formalism is just to note this important equivalence. So we find that the cohomology obstruction vanishes for a particular section if and only if we have a compatible family, but it's not just a compatible family of sections anymore. So this compatible family, well, okay, on the context that S1 belongs to, we have S1, but everywhere else we have Z linear combinations of sections. So just to kind of remind you of this, our notion of locality was that we could have a compatible family of sections everywhere, and now we say that the cohomology obstruction vanishes if we have a compatible family of Z linear combinations of sections. So clearly our definition of locality implies that we have a Z linear combination that works, but not necessarily the other way around. So this is why we have an implication that works one way but not the other. So we have these sufficient conditions for non-locality. Okay, from here I'm going to concentrate on examples. So hopefully this stuff will become quite clear when I see the examples. The first one I'm going to show you is the Hardy model. This is a case where we hit a false positive. So this is where our cohomological prescription doesn't quite work. Nevertheless, it's very instructive to see why this is. So the Hardy model is possibilistically non-local, which is to say that there is some section here that doesn't belong to a compatible family of sections. It's not strongly contextual. Not everything here has that property. So if I started with this one or this one, I could actually find compatible families. Okay, so the one I can't is this one that's in red. I think that comes out. Okay, so the one in the top left. So just to show you why this one witness is non-locality. Well, okay, so we want to look for a compatible family that this belongs to. So we want to choose a section from each context, from each row. So this is the one we choose for the AB context, which is 0 of the others. And now we look at the intersection of these two. So these intersect on the A measurement. So here we had A goes to 0 being the possibility, so we should have this also in the second context. So this means we need to have this one if we're going to have a compatible family. So we 0 the others. Again, similarly, we look at the AB context and the A-B context, so they agree on B. The B assignment was 0 here, and in order to have a B assignment of 0 in this context, we were forced to go for, B assignment of 0, yes, we're forced to go for this one. Okay, so 0 the others. Similarly, if we look at this and this, we find that they overlap on B dash, and we need to have this one here. So we set the others to 0. Now we've looked at the compatibility of the contexts all the way down except for the last two. So these ones agree on A dash, and we see that actually one of them assigns A dash to 1 and one of them assigns it to 0. So, so we conclude that there is no compatible family for this section. Okay, so this is where this is just to show that it is non-local. Now I'll show you how the cohomological prescription messes up on this. So I'm just going to label the non-zero sections. So just label them S1 through to S15, and leave out the ones that are not in the support at the moment. And I claim that a compatible family of Z linear combinations is this thing. I'm not going to go through this and show you. You can work it out yourselves if you're worried about it, but I'll just claim this is true. Okay, so the fact that we get this compatible family of Z linear combinations means that the cohomology obstruction vanishes. So false positives do arise. It doesn't pick up on non-locality in this case. So now I'm going to show you another example where it does work, and that example is the PR box. So we had this already. This is an example of a strongly contextual model. It's worth noting this because the examples that seem to work for us seem to be the strongly contextual ones. Strongly contextual, just to remind you again, means that no section in the support group is still compatible. Okay, so if we want to see if there is a family of Z linear combinations here, we're just going to give Z coefficients to each section in the support. So we just label them A through to H. Now we have certain compatibility equations. Okay, so if we restrict them on restrictions, we get these things. So just to tell you about the notation here, to make it neat, we wrote C1, 2 to mean the intersection of the contexts C1 and C2. That's A. Okay, so we get these equations for compatibility. What these amount to saying is that all coefficients are equal. Okay. However, if we want to check that a section is a member of a family, compatible family of Z linear combinations, it amounts to setting its coefficient to 1. So let's say we wanted to do A, we'd set its coefficient to 1 and B to 0. And then we look for Z linear combinations of everything else that satisfies this. Of course, this can't happen here because we've already got A is 1, B is 0, and coefficients should be equal if we had compatibility, so it messes up already. Just to say that the fact that we don't look at the fact that we zero everything else in the context that we single out, this comes from the fact that we're using the relative cohomology. I don't really want to get stuck in the technicalities there. Okay, so we conclude that there is no family of Z linear combinations extending this section. In fact, it's true for any of them. And so the cohomological prescription does pick up non-locality in this case. There are a number of other examples where it does work. These include the GHZ model, Merman square, as I said already, the 18-vector Kochen-Specker model. And we also have a larger class of Kochen-Specker type models. So I'll just, how much time do I have?
Say another 5 minutes.
Okay, cool. So I think that should be fine. So I'll just say something quickly about this class of Kochen-Specker type models. We've been able to do something quite nice with this, and I think this represents a step in the direction we'd like to go here. So the Kochen-Specker models, we have an outcome set of just 0 and 1. And we want to assign the outcome 1 to just a single measurement in each context. So sections in the support are precisely those with the single number. An example of this is, of course, the 18 vector model. So here I've left out the columns that have anything other than a single one because they just don't feature in the support. Okay, just to say here, the compatibility equations look like this, and we'll check that these have no solution. So there's a proposition in this paper of and Brandenburger, a necessary condition for this Kochen-Specker type models to have a global section. And so what is this is dm, so for each measurement dm is the incidence, the number of contexts that it appears in. So for example, every measurement appears in 2 contexts in this one. And u is this is the number of contexts. So here we get the greatest common divisor of a set of 2s, so that's 2. Does this divide 9? Because that's the number of contexts we have. Of course it doesn't, so then we find that the 18 vector Cochen-Specker model is strongly contextual in that way. We've extended this to this proposition, which I won't bother reading out for you. I'll just give you the corollary, which is to say that we find that the vanishing of cohomological obstruction is a complete invariant for this particular set of models. So it's any connected Cochen-Specker type model violating the condition of just so this is a class of models for which the cohomological description picks up exactly the right things. So we would like to extend this further. This is the kind of thing we'd like to do. So on that note, I'll move to speaking about just limitations and further directions. So as I've said a number of times now, the cohomological condition is sufficient but not necessary. We'd like to have, understand better which classes of models this works with. It might also be necessary to refine the presheaf that we work with, so that we get a finer invariant. So this is something that we've thought about, but we haven't come up with anything good on this yet. We have conjectured that under certain assumptions, we'll be able to find that the obstruction is a complete invariant for strong contextuality. So this is something that seems to be coming up from the examples we've looked at. And then finally, I'd say that we've been computing the obstructions by brute force enumeration. So if you remember this list of linear equations that I showed you that we got from the 18 vector Kochen-Specker model, we machine checked this. That was quite a long task. So we'd like to have a nicer way of going about this, of course. And that brings me to the end of my talk. So thank you very much.
Any questions?
So there's a contextuality proof that was proposed by Specker in 1960. It's proof that doesn't arise in quantum mechanics. And I'm wondering, maybe this is more of a common question, but it might be interesting when you're trying to come up with a framework for describing contextuality proofs to ask the question whether that proof can be described. So the way the proof works, are you familiar with it?
No, I'm not. But I mean, I think it could work in this field. This isn't restricted to quantum mechanics, of course. It's generalization of probabilistic models.
So it's a generalization that's a little bit different from, say, PR box type generalization.
Right.
Because in Specker's proof, he says, imagine you have 3 measurements for each binary outcome. So they call them A, B, and C. Now, in quantum mechanics, if you can measure every pair of them jointly, then you can measure all 3 of them jointly.
Right.
Because if every pair commutes, then all 3 commute.
Okay.
Specker says, imagine a world wherein you can measure the pairs jointly, but you can't measure the triple jointly. And so the PR box type thing doesn't have that feature. It's like quantum mechanics. It has the same structure of joint measurability as quantum mechanics does, but Specker's world doesn't. And so he zeros and ones to the three variables to get any computation for your pair, because no matter what zeros and ones you set down, there's always going to be correlation on one of the three legs.
Okay.
So maybe that's worth.
Yes, this would be an interesting page. Yeah, I think we could fit this in.
Yeah, this fits in. So it's just a triangle. So
Triangle?
yes.
Ah, okay. Okay, yeah, that's very
Much more context would be A, B, B, C, and this. And then A, B, C works. That's good.
Maybe we should try to figure it out afterwards.
Another question? Yeah,
In the case of your false positive, have you checked cohomology groups? If they give a melody
No, so actually, so I think higher order cohomology groups are not going to be much used here. So actually, since we're dealing with cohomology, the zeroth order group gives you global properties, and I think when you move up beyond this, I'm not sure how much use it's going to be. I think the kind of higher order things tend to be sort of tool for inductive groups and so on. So I'm not sure that would.
I'm not sure I can really translate what you do. Usually we would look for higher churn classes.
For higher
churn classes. It's not clear.
Okay.
Okay, thank you. That's next, yours, Nijmegen?
Yeah,
Utrecht, right.
Okay, thanks. Since I'm the last speaker before we're going to have dinner, I wanted to give a talk that is slightly easy to digest for everyone here. So before I start, I want to apologize for maybe at some point stating things that, well, in some parts of the community are considered to be elementary. So what I want to do, as Steve Vickers already mentioned, recently there has... Okay.
If you want.
Yeah, well, I'll just do this. So, as Steve Vickers already mentioned, recently there have been two proposals for a topos approach to quantum mechanics. One which is the imperial style and one which is the Nijmegen style. And the aim of my talk is to apply the ideas from these approaches to the realm of quantum field theory. And in particular, I want to show that while this topos approach to quantum mechanics gives a geometric flavor to quantum mechanics, you can also do this for quantum field theory, and then you get some nice geometrical things there. So, well, before I'll do that, first I want to discuss the terms that arise in the title, which is borification and local net. So let's start with borification. So this is the starting point of this topos approach to quantum mechanics. So recall that the goal of this approach is to give a geometric presentation for quantum mechanics, and in particular we want to find something which you might want to call a quantum phase space. And now the idea that During and Isham had, and which the people from Nijmegen have also considered, is to construct such a phase space internally to a topos. So how do we construct such a topos? Well, if we have a C-star algebra A, we assign to it a poset of commutative subalgebras, ordered by inclusion. And now, if we have such a poset, we can consider the co-presheaf topos over this poset, and we can endow it with one particular object in there, which is the co-presheaf that sends any commutative subalgebra to itself, considered as a set now. So this is a commutative ring, and actually it's even a commutative C-star algebra internal to this topos, but I don't really want to consider that. I just want to consider this structure as a ringed topos. So now, Heunen, Landsman, and Spitters basically have the result that this ringed topos provides a good universe in which you can do quantum kinematics. And in particular, internal to this topos, you can formulate or you can construct a quantum phase space, which is somehow dual to the internal ring that you have. And now, Steve Vickers has kind of argued that if you do this, then actually you don't really need the topos anymore, and you can just consider bundles. And what I want to do is somehow the precise opposite of this. So what I want to do is not consider this internal phase space, and just consider this ringed topos. So from a different perspective, we now have a ringed topos, and recall from algebraic geometry or something that ringed toposes describe spaces. So this was the main idea by Grothendieck. Ringed toposes should describe spaces. So you can also say that you now have a ringed topos, or a space, that completely describes your quantum system. So maybe you don't want to call it a quantum phase space, but at least it's a space that completely defines your system. And basically, that's all I really want to use here, that there is such a ringed topos that you can assign to every quantum mechanical system. So, well, if you do this construction, the construction of this ringed topos, which in the literature is called glorification, then you can see that you can extend it to a functor, to a contravariant functor, from some suitable category of C-star algebras to the category of ringed toposes. So recall that a morphism of ringed toposes consists of a geometric morphism, so that's the topos part, and then a ring morphism between the pullback of the ring in the codomain to the ring in the domain. And it's precisely the direction of this ring morphism that forces you to make this functor contravariant. And if you want to make it contravariant, then you have to do some fiddling with the category of C-star algebras that you're considering, and you have to impose this condition that it should reflect commutativity. So basically, this is all I need from what has been done until now. That there is such a functor which assigns something which you might want to consider a space to C-star algebra. So now I want to turn to the second item which arises in the title, which is that of a local net. So local nets are used to describe quantum field theory. So now there are two main formalisms in the market for formalizing QFT. One is this topological quantum field theory. So this is something highly geometric. And the other is algebraic quantum field theory. So I want to focus on the latter. But the idea is that you want to describe a QFT on the spacetime X by assigning to every open in your spacetime an algebra of observables. And these observables should, or these algebras should somehow represent what you can measure in this region of space and time. And now obviously your spacetime has a causal structure, and you want this assignment to respect this causal structure. So very shortly, what is this causal structure that you have on your spacetime? Well, your spacetime is usually something like a Lorentzian manifold. So in particular you have certain classes of paths in your spacetime, which you want to call time-like or light-like. And the idea is that any physical reasonable signal that you want to send throughout your spacetime, it should move over such a path. Maybe except if you want to do tree notes or something like that. And now if you have two opens between which there are no such curves, then from a relativistic point of view they cannot influence each other. So then we say that they are space-like separated. So the example to keep in mind is the simple Minkowski R2. So if I have such a basic open here, then everything that's space-like separated from it lies in this range here and in the right range. So in particular, the square that I've drawn in the right is space-like separated from the other diamond. Okay, so now what is the mathematical definition of your QFT. So it's a local net. So this should be a co-presheaf on the opens of your spacetime to the category of C-star algebras with inclusions between them. So the idea is that if you have an open and it's contained in a larger open, then obviously everything that you can measure on the small open, you can also measure it within the larger open. So inclusions of opens should be mapped to inclusions of algebras of observables. So, and then you want to relate the causal structure on your space-time to some kind of causal structure that you have in quantum mechanics. So now what you say is that if two opens are space-like separated, so they cannot influence each other, then the corresponding algebras should also not influence each other, which means that they should commute. Right, is this clear? Okay, so this is somehow this is basic mathematical stuff. So if you really want to do physics with it, you have to impose way more things like existence of a vacuum or positivity of energy or something, things like that. So now if you look at this definition from a mathematical perspective, one thing that's a bit odd is the fact that it doesn't really use the fact that your space-time is a topological space. So there's usually, if you want to construct things like this on a topological space, you want them to be sheaves, or at least you want them to satisfy some gluing condition. And well, obviously you don't see that here, and in fact you don't even see the notion of a cover here. So from a mathematical point of view, this is a bit weird, especially if you also have a highly geometrical formalism for QFT. And also from a physical point of view, this is a bit weird, because in physics usually QFTs are described by, I don't know, PDE systems, which are in some sense geometric, right? So now, one thing that people usually do in the literature to, well, at least add the notion of a cover to your axioms is impose a condition called additivity. So the idea is that if you have two opens that are next to each other, but they have to be space-like separated, then they generate, then the algebras corresponding to them generate the algebras of the larger open. So, okay, now we have covers, so that's nice. But still, if you look at it, it's still not really geometric. So, still there are not really nice gluing properties for A. And the main reasons for this are, well, first of all, this local net is a co-presheaf. So usually you want to describe presheafs on a space. Okay, this is not very important. You can add ops at various places to get on. But what's more important is the fact that you now have a causal structure on your spacetime, which is somehow an extra structure that's not really measured by just basic topology. So you have to be careful. You should match it somehow with glue. And the final, and that's actually the most important obstruction here, is the fact that your net is actually local. So if you want to try formulating something like a co-sheaf condition here, then you see that the fact that algebras that are assigned to opens that are far away from each other, that they should commute, that somehow forms an obstruction here. So now my claim is that if you use the borification construction that I mentioned earlier, then you can somehow resolve these issues, and you can get some kind of clean geometric description of a QFT. So that's nice, because then it relates to the other formalism for QFT that you have, and especially relates to your spacetime. Okay, so what do we do? Well, if you have a net going from the opens of X to the C-star algebras with inclusions between them, and first we can dualize everything. And now you may note that an inclusion of C-star algebras is one of those particular morphisms that reflect commutativity. So this means that I can post-compose with the borification functor that I described earlier. So now, well, for consistent terminology, the resulting object you might want to call a borified net. So in particular, you now find a presheaf of spaces on your spacetime X. So the Co is already gone here. So explicitly, if you have an inclusion of opens, then you find a geometric morphism going to the left in this case between the two ring toposes, and you also find a ring morphism. So now this borified net relates quite nicely to the locality condition that you have on your original net. So what you can show now is that a net is local precisely when for two space-like separated opens you have that the induced morphism from the borified net evaluated at the total space to the product of these two spaces. But this geometric morphism now is an extra right adjoint. So somehow already algebra is commuting, you can now translate it into a geometric statement, right? A geometric morphism having an extra right adjoint. But now there's still this sentence, two space-like separated opens, and we want to formulate this in a more topological way. So how to do that? Well, we need to consider a hypersurface in our spacetime, which you might want to call a Cauchy surface. And the idea of a Cauchy surface is that it behaves like just regular space at an instant of time. So, if you have such a surface, and you have an open in the surface, then you can assign to it a principal open in your spacetime. Kind of in the way that I did it here. If you have an open interval on this curve, then you can assign to it the smallest diamond containing it. And now you can define the restriction of your borified net to this surface by the following basic formula. So this is nice because this allows you to eliminate the statement space-like separated from the result I just showed. So now the statement becomes, if you have a local net, or A is a local net, precisely when for any Cauchy surface and two disjoint opens in there, you again find the statement that I just wrote. This geometric morphism has an extra right adjoint. So being space-like separated, you can now formulate in being disjoint, which is a purely topological statement. So now finally I want to get to the main result, which is the actual gluing that I promised. So the theorem now is that if you have an additive local net, right, from the opens of your spacetime to C-star algebras with inclusions between them, then being additive and being local precisely translate in the following condition. So your borified net now has the property that its restriction to any Cauchy surface satisfies descent by local geometric surjections. So what does this mean? If you have a Cauchy surface and you have an open in it and you cover it by some other opens, then, well, as always, you get, when you formulate sheaf-like conditions, you get a descent morphism, which in this case is a geometric morphism, going from the borified net at U to your gluing data. And now this descent morphism has again an extra right adjoint, just as in all my previous propositions. But moreover, this right adjoint is full and faithful, which implies that the left adjoint is also full and faithful. And this is precisely the definition of a local geometric surjection. So now how should you see this? I think Urs already mentioned this in his talk. Local geometric surjections, or geometric morphisms, somehow model infinitesimal thickenings. So somehow if you have a topos sitting over just over the point or over set by a local geometric morphism, and your topos models a thickened point. So what this means is that these purely AQFT kind of conditions translate to the statement that your Borifide net restricted to a Cauchy surface is infinitesimally close to being a sheaf. So, concluding, basically we already knew that you can use topos theory to give a nice geometric presentation of quantum kinematics. That's what Heunen-Spitters and Landsman have shown. And now, what you can also do is you can use it to give a nice geometric description of algebraic quantum field theory. So, I guess that's it. Thank you for your attention.
Any questions? Yes, perfect.
Usually this game of algebraic quantum field theory, as it is done by, say, Friedenhardt and Koch and these people, you assume local hyperbolicity and formulation and all these type of things. So, do you have a chance to put the metric on your space and all these other things which you actually need to come up with a quantum field theory in curved space-time?
That's a good question. Yeah, I don't know. At least what I should mention is that this result, right, as I now stated, it looks like this works for any space-time, so with any metric, and that's not entirely true. You do have to have some nice topological properties of your space-time, because you have somehow restricting to a Cauchy surface should remember all the info. So if you want to apply this to any curved space-time, then you get into trouble.
But you need at least something like global.
Yeah, right, precisely. Yeah.
Any more questions? No? Thanks, Tim. And it's dinner time.
Have you typed it up? Is there something written?
Yeah, you can find it on the archive.
Oh yeah.
If you Google my name, so it's the only thing I've produced.
Because I was a colleague of Rainer Förch in Leipzig, and we had lots of discussions about these things over lunchtime. And Mario Paschke, who is no longer in physics, was also there. And there was a following idea which you possibly with these tools can better solve than these people with the actual algebraic quantum field theory on which actually want to compute physical things. This algebraic quantum field theory is a functor which assigns to a space operator algebras.
Yeah.
Now what you actually want to do is something different. You want to study what non-commutative space actually is underlying this quantum field theories. Yeah? Because if you put artificially a space and say, oh, it's a classical space-time, then you end up with something, a quantum field theory sitting on a classical space-time. That's not quantum gravity. Yeah?
Right.
So what you actually want to do is much more like in algebraic geometry, where you do it with a functor in the opposite direction. Yeah? Right. So actually, I would like to see, since you have these co-presheafs, so if you turn out the functor the other way around and say, okay, I'm not interested in producing operator algebras, what I actually have is an operator algebra. I want to produce what kind of non-commutative spaces live on the other side. Yeah? So if you op your category, make from your co-presheaf or presheaf on the op thing, turn the functor the other way around, do the op purification, so to speak, you possibly could end up defining what a non-commutative space derived from a general so I'm not sure if you're really talking quantum field theory here, but that you do actually derive something, say, of a part of quantum field theory, what kind of non-commutative spaces you would actually see.
Right.
And Rainer Völk and Mario Paschke did at least 2 papers. I'm not sure if they. One is on, at least online on the archive. The other I do not know if it's finished. Yeah, because it's going on for 2 years or 3 years or something. They tried to do this for the Dirac theory. Yeah? So they wrote down this algebraic quantum field theory on space-time, used all these machineries for the Dirac theory. It's tremendously complicated. Yeah? But they managed to do this and to get quantum field theory and showed that it actually works, at least for Dirac field. Yeah? Three Dirac fields. Yeah? So it's not much. But they showed it works, so there's a hope actually that using this type of thing, you could give a much deeper foundational approach to what actually is non-commutative geometry, also in the concepts, without using the somehow flawed, I think, spectral triple approach. With the spectral triple somehow implies already some structure on a classical underlying manifold, and it somehow artificially puts this non-commutativity by using these matrix factors.
Whose glasses
So
are
in
these?
this sense you could start,
Who left his glasses?
in this sense you could start out with the operator algebra at will, so to speak, if it's
these your
or not,
glasses?
yeah, and try to reconstruct what categories, spaces, whatever that is, non-commutative on the other side appear, like in algebraic
Can we
geometry,
have
you
a
define
shit-
algebraic varieties just by functor.
Can one of you shut down the camera?
And you should
Are
have the
used
same
to-
direction
you
as in
know how this
algebraic
works?
geometry, not the other way around. Yeah? And the physicists only like it this way because they know how to deal with operator algebra. But the interesting picture in my eyes
What are these videos to be put on some webpage?
Yeah, I think the Oxford Video Archive or whatever, they'll end up on that.
Oh, there's an